Since today is the coldest day of the year so far in southern Ontario, Canada, for 2009, I think I'll make an appropriate video. Damn, it's cold outside. Squeaky snow. But not like Winnipeg, where they're experiencing -40 right now Celsius. Right, kitty? So even though this video is about firewood, it's really about oxidation and chemical bonds created by the sun. In our universe, we basically have two kinds of energy: nuclear energy and the energy created by the sun. And energy cannot be created or destroyed, it can just be changed to different forms. So that's how we can explain stuff on this video. Nuclear fusion is like what's happening in the sun. That's when two elements, namely hydrogen, are squeezed hard enough together and with enough heat that they overlap each other and become a new element called helium. And that overlapping is giving off the space that's no longer needed in that new structure, and that's energy. In fission, like in a nuclear bomb, that's atomic decay. That's when atoms are breaking down, or elements, and energy is released by nuclear decay and a new substance is created. So the sun's nuclear fusion is creating all the energy that's landing on our Earth. And that energy is heat and light and electromagnetic spectrum. But of course, if the energy couldn't dissipate at almost the same rate that it's coming in, the Earth would burn up, just like if the sand just kept getting hotter and hotter. Luckily, the energy is just reflected into space, just floats around out there, and maybe eventually gets sucked into a black hole or into another sun. A small fraction of that energy is converted by photosynthesis. That's what plants do, or photosynthetic plankton does, to convert the sun's energy into biomass. Everything can be used on Earth by plants and animals, because biomass is what drives the world. Now the kind of biomass we're talking about today is firewood. Now we all know a forest is cooler than a desert. Well, of course, a desert receives the sun's energy and eventually has to reflect 100% of the sun's energy, or it would eventually burn up and evaporate and, vaporize. Well, a forest is cooler for the reason that plants are very efficient at absorbing the sun's energy and turning it into biomass. They can absorb up to 7% of the heat and light coming from the sun and convert that into solid state matter. So like we learned many years ago in school, photosynthesis is the trick. The plant takes carbon dioxide from the air, which is 1 carbon and 2 oxygens, and it takes water from the ground, which is 2 hydrogens and 1 oxygen. Then it combines them together, and that takes energy, and the sun is that source, and it stores the energy in the chemical bonds of combining them together and making hydrocarbons. Plants don't just make hydrocarbons, they make similar things like sugars and carbohydrates, which are like starches. They have many different ways to store the sun's energy. Now, to release that energy from biomass, in most cases you need oxygen, but not in all cases, because there's a thing called anaerobic decay. That means decaying without oxygen. Anaerobic decay occurs at the bottom of the ocean and usually produces natural gas. It also occurs at the bottom of swamps, underneath coal beds, in oil deposits, and in your own intestines if you're a living creature. Now, oxygen is a free radical. It means it's unstable. It likes to attach itself to other things. It just doesn't want to exist by itself. It doesn't even want to exist as an element in its elemental form, as ozone, O1. If it does exist in that state, it's lighter and it floats up to the top of the atmosphere and protects us from some of the sun's rays, but it would prefer to be O2. O2 is still very highly reactive. Of course, if you get a high enough energy level, things will spontaneously combust, and that's called fire. Now, the fire and heat that's produced from burning firewood or any other biomass or fossil fuel is exactly in direct relationship to how much energy it took to create that biomass. The same amount of energy it was absorbed by the sun as light and heat is then given back off as heat and light, but more so heat when you burn stuff. Now for the unusual thing. Oxidation occurs slowly by itself without fire too. That means when wood decays or any biomass decays and turns back into, carbon dioxide and water again, exactly the same amount of heat is released as burning it in a fire. But that might take 10 or 20 years or even longer. So we don't even notice heat is produced, but in a greenhouse kind of way, it produces no more energy or heat by burning it than it does by rotting. It's just a longer process. Every time something is oxidized, there's chemical bonds being broken and new ones being created by oxidation. So, example, when your car is rusting and rust is formed, that's creating heat. And the rust actually weighs more than the original piece of metal because now we have several oxygen atoms attached to it. An accelerated form of oxidation is a cutting torch on steel. Once you get a hot enough fire in one spot on the steel where the steel starts to melt, all you do is squeeze the trigger with the torch, inject oxygen, you can shut the fire off, and the torch will continue to cut the steel by oxidizing the steel, and the steel produces a lot of heat. They also use this in an oxygen blast furnace, where they stick a hollow tube in a molten pile of steel with unmelted steel too, and they use a little bit of electricity to start an arc, and they inject oxygen, and the burning steel, or oxidizing steel, creates enough heat to melt the rest of the steel. So every time you're enjoying your roaring fire or the heat from your methane-powered natural gas furnace, you're just enjoying some stored sun's energy that, for example, from a furnace could have been stored for millions of years ago, and in your fireplace could be hundreds of years old or just a few years old. Now with anaerobic decay, there's no oxygen involved, obviously. So that decay is not complete. And since it's not complete, there's always some energy left over. Of course, some heat is produced, but some energy is left over, and that's most often left over in larger hydrocarbons, like in oils that are like in crude oil that's under the ground, or very commonly natural gas, methane. Now we consider those very usable energies because they're of a simpler form, and they can be easily, changed or modified in the petrochemical process to make them very suitable for life on Earth and powering our industrial world. In our bodies, heat is created in two different ways, by oxidation and by anaerobic decay. A certain amount of the heat your body produces is just coming from anaerobic decay within your intestines. Oxygen is carried through your bloodstream to oxidize similar things like sugar. And for example, did you ever notice when you're thinking a lot, you have to pee more often? Well, that's because your brain, when you're thinking a lot, uses a lot more sugar, and that's what your brain runs on. And when you oxidize sugar, you get carbon dioxide and water. When your muscles work, they use sugars and similar things too, and heat is also produced in the same way by oxidation. So yes, Al Gore is right. Certainly when you burn fossil fuels, or firewood, or any biomass, greenhouse gases are created. But when you're burning something that was just found on the surface of the earth, which is biomass or wood, you're not actually changing any equation for greenhouse gases and how the world's going to heat up or something like that, because it would have happened anyways. When that wood or that biomass completely decays, exactly the same amount of heat and greenhouse gases would have been released as if you burned it today. It just takes over a longer period of time. Hearing that, you would never think we would have enough oxygen to breathe, like spare oxygen, because it always seems to be a balanced process or equation where decay and creation are equal. Well, luckily on this Earth, it's not an equal equation. There's the oceans. 70% of our oxygen is produced in the oceans, and that's a one-sided effect. Those photosynthetic planktons that produce most of the oxygens, which are near the surface of the ocean in warmer seas, when they die, they fall to the bottom of the sea, and usually the sea is so deep there's not enough oxygen. So they just lay down there, making the equation one-sided. They produce oxygen, but they're not decaying and producing carbon dioxide. They may be breaking down and producing gas hydrides, which is actually just compressed or liquefied natural gas, which is under the ocean, but that very often doesn't escape. You burn fossil fuels, whether that be coal, natural gas, or oil, you're actually releasing the stored sun's energy from millions of years ago. I think that's pretty cool. So when you actually see a fire burning next time, pay closer attention. The flamey stuff is mostly the hydrogens being oxidized, and the yellow glowing coal stuff is the carbons or the charcoals being oxidized. Pretty interesting now that you think about all this. Enjoy.